Hello and welcome back. My name is Brandtberg and I'm your moderator for the rest of today. So now we're going to have a keynote dialogue. Earlier this year, Dean of School of Architecture from the Royal Academy of Copenhagen, Jakob Knudsen, received the honorary award from Nykredit for his work on, among other things, the Makoda project. The jury wrote, Jakob Knudsen's contribution makes a difference for a better and healthier world. His work is an inspiring example of how an architect from a rich and privileged country with insight, talent, and generosity can make a notable difference in parts of the world where basic living standards are not always possible. The jury continued, the built environment almost becomes a medical intervention. It is my huge pleasure to welcome Jakob Knudsen.
Good afternoon, and thank you to VELUX for inviting me. I'm really happy to talk and to bring you into my work about healthy architecture and how we can work as architects for evidence-based approach to architecture. What I'm showing today is mostly from Africa, from Tanzania and other places, but let me start this place. When we think about health, we often think about something which has to do with doctors or hospitals or treatment. But in fact, a lot of health has to do with the building, the house we're living in, our physical condition. As an example here, I have a diagram showing the top 10 causes of death in Tanzania. AIDS is probably not related to the house, but lower respiratory infections, diarrheal diseases, and malaria are all important diseases directly connected to the building, to the house. We tend to forget this. It has been the same all over the world, but a lot of the improvement in life expectancy is due to engineering and architecture in combination with medical science, of course. I've looked a lot at malaria. It was a kind of a coincidence I came into this, but malaria is one of the big diseases in the world. There's at least 400,000 people dying every year from malaria. There's millions of cases, and it's a really terrible disease for a lot of people. There's also a lot of other diseases connected with mosquitoes. Malaria is transmitted by mosquitoes, and if you think about Zika and dengue, these are also diseases related to mosquitoes. Malaria is mostly prevented, or best prevented, by using a bed net at night. This is a picture from the Gambia. You can see this man, he has a bed net. The problem is that the house is completely without ventilation. When he closes the door, this house will be incredibly hot at night. So we know that this is a big problem. We can see that in a lot of studies, the biggest reason for people not using the bed net, which is preventing malaria, is discomfort. It's too hot inside the building. So we started to look at this some years ago, me and a medical doctor. We became friends in another project where I was building a lab. I met this medical doctor, and we started to talk about houses and health. And we came up with this project looking at the indoor changes caused by bed net. This is two women using a bed net for fishing, not because they're ignorant, but because they're using it for something useful, as it's probably too hot in their house. We looked at Tanzania and the Gambia, and we looked at the heavy houses of Africa, tried to understand them, tried to use the tools of architecture to get into the houses and understand the climate. We looked at these heavy houses made from burn bricks and soil bricks. We went into the houses, we looked at the bed nets, we tried to understand why are these houses so hot, why are they having so little ventilation. A house like this from the Gambia is very beautiful, but it's also probably 40 degrees Celsius inside. It's extremely hot. This one is from Tanzania. It's better ventilated. It's kind of not usual. Most houses are without a lot of ventilation. And then we compared them to Thailand and the Philippines, because we knew that there was an architect in Asia which was kind of fundamentally different, but in the same climate, and we tried to understand this. So we looked at these traditional houses in Thailand, kind of lifted from the ground, made from light materials, very reasonable houses, very comfortable houses, even though they were made from very cheap materials. This is one of my favorite pictures. It's from Thailand. It shows a bamboo house. You can see how air and light is coming in through all cracks. You can almost feel how comfortable it is to be inside this house. And again, we found the same in other houses. This is from the Philippines. Similar house, similar construction principles, very different from the similar African houses, which are kind of made from heavy materials placed directly on the ground. So we looked at it, we measured a lot of houses, and we looked at temperature and a lot of other parameters. We tried to understand what is the difference, and we could see that the temperature was much hotter in the Gambian and Tanzanian houses compared to the Philippine houses and the Thai houses. And then, of course, we were looking especially at the temperature at night, at 9 o'clock, because that's when you decide to wear a bed net or not when you go to bed. And we could see that some of these houses were incredibly hot and others were more comfortable. We started to model these houses, both physical to make experiments, kind of rebuilding houses, and we started to make digital models, and we could digitally kind of turn an African house into an Asian house, and in this way understand the differences. We concluded all this in a book about kind of showing all the differences between Asian and African houses, and this was the starting point for a new project where we thought we need to start building some of this and kind of demonstrate what are the different effects. And we did this in a Tanzanian village named Magoda. So we wanted to look not only at malaria, but also at other parameters, like indoor smoke, for instance. So you see here how a woman is cooking, and there's a baby sleeping over here on the other side. There's lots of smoke inside the house. It's a major health issue in Africa. We also looked at food security, kind of how do you store your food, how do you have a good food hygiene, how do you get enough water. We looked at all the wells, how to improve the entire environment around the house. And we came up with this kind of diagram. We thought, let's make a house where we raise the bedrooms, kind of make them Asian. Let's have a storage area, a cooking area, an improved cooking area. This is outdoor. Let's harvest water and make a better latrine and kind of combine all these health initiatives. We made a digital model, and then we started to build. You can see how the bedrooms are raised now. We had a lottery because you can't just start building houses in an African village. You can't just hand out houses. So we thought we need to do it in a kind of controlled way. So we handed out houses after a lottery. And this is one of the first houses. It's a house made from bamboo, which is normally not a building material used in this part of the world, but we found it and we started to build with it. We also built all the houses in two-story editions, kind of to test different geometries, the same size, but different geometries. This is from the inside. This is another picture from the inside. This old man is living on the upper floor. We made it in a version also from wood, kind of making using wooden planks or boards, but spacing them so that you would have air moving into the house, again seen from the inside. And then this is the most radical, where we used netting material, kind of shade net, the same you use around building sites to protect the buildings. And we started to use this as a building material, different types, and this was quite interesting material to use, and people really, we found it to be very useful. So this, of course, gives a lot of ventilation. You can see there's a lot of air here. That's kind of unusual. It's because we put a lot of light inside, but it creates very good ventilation and works very well. So we compared to traditional houses, and we also tried to modify some existing houses to see if we could make them perform as well. We did also new latrines, and we improved the water supply, and we made better cooking areas. And then we started to measure, and we could see here that there was a huge reduction in our new houses on mosquitoes. So we kind of, we measured how many mosquitoes that would be inside the house. This was the combination of biologists and medical doctors and architects working together. So you could see that especially the two-story houses had a 90 to 100% reduction in mosquitoes inside, much better than the control houses and the reference houses. And we also measured the indoor comfort using the tools of architecture and engineering, and we could see that the new houses were performing much, much better. So we couldn't help doing a few more prototypes. So we had carpenters from Thailand flown in, and they built a bamboo house, a traditional Thai bamboo house with an African flavor. And we kind of concluded all this in a last prototype where we had a kind of a space on the lower floor, which was an open social space and a cooking area, and then 2 bedrooms on the top floor. This is the area below. It's kind of completely protected against mosquitoes. At the same time, it's also a very practical cooking area. So we used the tools to disseminate this. We published in a lot of, like this one from the Lancet, I mean, in medical papers, and we took it also to more public sources. We took it to Venice, to other exhibitions, to the Venice Biennale, and kind of tried to get it out, not only to architects, but also to medical doctors and biologists and everybody else who were interested. And this created actually a lot of interest, and we were suddenly involved in also another group looking at the big changes in Africa on urban planning, and we used data from large sources to try to say something about the development of housing in Africa. And we published this article in Nature where we could kind of demonstrate how there was a lot of improvement in houses in general in Africa, but also still a lot of slums. Another thing we could see from these data was that all the roofs in Africa are changing, so that suddenly there's a lot of metal roofs. And we started to speculate on this, and we could see that it's changing very rapidly. And we kind of demonstrated in another Nature paper that there's a connection between metal roofs and the number of mosquitoes and actually malaria transmission. So suddenly there's a very direct connection between the way we build houses and how many people get malaria. This was kind of unexpected, but it turned out that there's a number of ways that the houses are connected to diseases. In another article, we could kind of see that there was a kind of direct relation between housing and not only malaria, but also diarrhea and growth failure and anemia and other stuff. So suddenly it was kind of expanding. So this was a very cross-disciplinary work where I was using my knowledge as an architect to help medical doctors and biologists to discuss this data. How can we understand this together? We also made very basic studies, like, for instance, if we want to raise a house, how high should it be? And we made these houses where the house is kind of lifted, it goes up and down. So we placed 4 houses next to each other, and we could have them in different positions, and we could see how many mosquitoes there would be inside the houses. And we could have this perfect curve where you could see that we had a 90% reduction from raising the house without using any netting, without using any chemicals, just geometry. So this is pure architecture. We can use this to kind of to lower the amount of mosquitoes. We looked at windows. Again, we could see that there's a need for new windows, but we could also see that if we make smaller windows to prevent mosquitoes from entering, there's actually more mosquitoes coming in. The bigger the windows we make, the less mosquitoes we get in to the house. This is kind of counterintuitive, but it has to do with carbon dioxide, that it comes out in very small concentration if it's big windows, and the opposite if it's small windows. So the geometry of the window is important. And we also looked at doors, and I don't think I will go much into it, but we had a project where we built a lot of houses in West Africa, trying new designs, and it was very disappointing. We couldn't get any good results. We actually failed. There was no protection against malaria with this project, and it probably had to do with the quality of the building components. Like, these are the doors. They were too bad. So we made another project where we tried to improve these doors and come up with new suggestions on better doors, kind of ventilated doors. Trying to combine the knowledge we have to come up with different approaches to keep all these mosquitoes out of the windows, out of the houses. So today we are now in a new project where we are looking at the 3 big killers of children in sub-Saharan Africa. We're looking at malaria, respiratory tract infections, and diarrheal diseases. So we're trying now to combine all the knowledge we have, trying to get in all the information we can get. And we have kind of made this a model, or this platform, you can say, as a house, looking at a lot of different parameters of the house and trying to optimize it. We also found it quite useful to work with the sustainable goals as a kind of an indicator on different ways to approach it. And of course, good health and well-being and sustainable cities and communities are kind of key things, but we can also kind of find them again in a lot of the sub-goals. At the moment, we are making the first randomized control trial, to my knowledge, where you're actually using new houses to try to improve health. So this is what you do with medicine or medical interventions all the time. But to my knowledge, it has not been done with architecture before. So we are building 110 new houses in Africa, and then we are trying to see what is the effect on the children living in the houses compared to the children in the houses next to it. So we have 110 new houses, and we have 404 existing houses. And then we take 3 children from each house, so we have more than 1,650 children, and we're going to follow them in 3 years. They get this new house, and then we see what happens to them in terms of health. So we have, and then we're looking at a lot of other parameters. We're looking at entomological assessment, that is mosquitoes, how many mosquitoes get into the house. We had a lot on architectural surveys, indoor climate, temperature, humidity, air pollution. We are kind of moving into air pollution also now a lot. And then we are using social sciences to look at acceptability, and we are kind of looking at all the things around the house. How do people like the houses? What are the problems with them, and so forth and so on. We have these houses built in an area, kind of distributed in 60 villages. It's an area of probably 60 kilometers by 40 kilometers in south of Tanzania, just on the border to Mozambique. We started out building prototype houses. Again, we built in different designs and materials to test out what is best for this particular area and these problems. And we came out with this model, which is kind of a new edition of what we've done before. So we have a ground floor with a cooking area and a storage area. We have an upper floor with 2 bedrooms. We have water collection. We have a good latrine. And we are trying to kind of get all these, we have solar power and other things. These are from our test sites, 2 different versions of the house we chose to build in the end. This is from the inside. It's all very light. What appears to be windows or walls here are all netting. So these houses are made from incredibly light materials. It's all what is now, it's a steel system. It's a light steel system made locally. It's made directly from our digital models. It rolls out in profiles. It's cut to size. It comes as a set. You can assemble the whole thing in a day. I'll show a picture in a while. And you can see what looks here like windows is actually just this netting material. What looks like concrete here is just 1 centimeter of a strong plaster on a net. So the thermal mass of these houses is very low. We can see that when we compare it to a local house in a village, we're using 30 to 40% less embodied energy and carbon, and 70% less concrete. So it's quite affordable also compared to existing houses. So now we have built these 110 houses. We just handed them over this summer. This is one of the houses close to the beach. You see the existing houses next to it. We hand them out after having a lottery. We examined 16,000 houses to find the houses suited for this. So we have been around in all these villages, went around to each house, took pictures, interviewed people, had measurements, had all these details. So we had a huge database of knowledge we are also using to kind of look for general other patterns in the area. We have lottery. In this case, it was this young woman who won the house. But we went around to all these places. We had lotteries. This is another couple. You see an existing house, which is kind of going to be demolished in the end. These are the 110 winners from all over. 110 houses, actually a lot to construct in a rural setting in Tanzania. It's not so easy. This is from the building process. So we make a concrete base. We have this steel system made from very light materials. We can put this up in a day or 2, and then we can continue. This is how it looks when it's finished during daytime. You see the water collection on the back and the chimney. This is a kind of a very open site. It varies a lot. This is from night. You can see how you can see through, but it's still kind of protected. This is a more in a village setting where it kind of fits into an existing semi-urban fabric. Another one from a village where you see how it's used. We have this small bench here, which is typical for the area. This is the water harvesting system, a young girl getting water. This is from the inside. We have this improved cooking area, so we can actually save more than half of the wood you would normally use in this way. And we can get the smoke out of the house. And this is what it's all about. This is the upstairs bedroom where this woman has put up a bed net, but also put up these curtains for privacy. And then, why should all this work? We need it to work because actually we know that we need to build 2 billion houses for 2 billion people in Africa in the next 30 years. That's 1.3 billion new people, plus half of the houses already existing needs to be replaced. So this is one of the very big environmental challenges in the world in the coming years, that we need to build houses in Africa and airports and roads and everything else. If we go back in time, houses in Africa looked like this. This is 100 years ago. A lot of the houses look like this still. But also some of the houses look like this. This is kind of forgotten, but there used to be houses in Africa that looked like the ones in Asia. They somehow disappeared. But we can also see that when we start to build examples, new houses are built where local people take up the tradition, are kind of inspired by ours, use the materials and do it in another way, but very similar, using the same principles. And then, of course, it needs to be good, it needs to be aesthetic, otherwise people will not use it. So in the end, there's been a lot of people involved in these studies, people from Oxford, from Thailand, from Tanzania, from Durham, and most of it has been supported by a foundation from Singapore, the Hanako Foundation. Thank you.
Thank you so much, Jakob. That was absolutely really inspiring and impressive. Please join me up here, and we'll have a dialogue afterwards. For now, I will introduce our next speaker, Seda Kacel, Madame Curie, postdoc researcher, and with the focusing on smartness, health assessment, and performance evaluation. Welcome, Seda. And please.
Thank you. Good afternoon. Today I want to present you the SHAPE project. The research is funded by the Marie Skłodowska-Curie Actions of the European Union. I started carrying out the project at UCLouvain, Belgium. The research is supervised by Professor Sergio Altamonte, and we are carrying out the research in partnership with VELUX. Climate change mitigation also would improve our air quality and health. COVID-19 showed us how important our indoor climate is for our health. It also evidenced that we need to change the way we use, renovate, and operate our buildings. So a new holistic building performance evaluation is needed, and considering subjective evaluation, user friendliness, user acceptance, and their lived experiences. And it should be, or these should be analyzed qualitatively and quantitatively. So from this holistic point of view, the SHAPE project aims to develop a new tool to evaluate health and smartness in nearly zero-energy buildings. And user comfort, health and well-being, energy efficiency, and smartness will be monitored and tracked holistically. The research methodology is four-stepped. So in the first step, we will build a framework of performance indicators. And at this stage, we will adopt metrics and methods of different disciplines. So for example, health sciences, behavioral sciences, environmental psychology, business organization, and sensor technologies. In the second step, the SHAPE tool will be developed. The tool is planned to have two subtools. So first an assessment subtool and then a decision support subtool. And in the third step, the tool will be tested and validated in real occupied residential buildings. And the second and third step will be done in collaboration with VELUX. And these collaboration will be mainly through my actual and active secondments at VELUX. And at the fourth step, we will develop a dissemination, exploitation, and communication strategy to disseminate the tool as wide as possible to a wide audience. And also the tool's integration into policies, standards, and regulations will be proposed. The impact of the tool is multifaceted, so promoting healthy and energy-efficient buildings, policy making for health, raising awareness of end users for healthy buildings for themselves, and also improving intersectoral collaboration and sharing knowledge between research and industry, and also highlighting how important multi, inter, and transdisciplinary work is in our profession. Thank you.
Thank you so much, Seda. Please join us. So, and I know because Jakob, you have an abundance of empirical data, and Seda, you are embarking on collecting all of this empirical data. But both of you actually address the cross-disciplinary endeavor, and I find it relevant, Jakob, because you also mentioned that you have biologists, you have doctors, etc. Some of the benefits of working in that way, I think, would possibly be very nice for Seda also to hear at this point.
Yeah, I think it starts with curiosity. That I mean, it's all about discussion. For me personally, it was just this discussion with a very good medical doctor, and we started to discuss the role of architecture and health, and then it kind of expanded. And as we gained more knowledge, we started to discuss with biologists, and then you need a social scientist, and then you find out. So it's kind of it's interest driven. Suddenly you need a statistician, and I think this is to the core of research, that it's not about you. We heard about the T-shape earlier today, and I think it's, to be cross-disciplinary, you need to bring something to the table, and that's. I think what we can do in these terms is that we can kind of use our own tools, but we can kind of take them to others and kind of demonstrate them. For instance, if we talk about malaria in houses, for many years, people have been looking at indoor climate. And this has been biologists and medical doctors doing this. And so they have used these kind of maybe a bit simple questionnaires asking people, do you feel hot or not hot? So what we did was that we took the kind of standard tools from engineering and architecture, the ASHRAE tools and similar, and said, okay, let's use them and kind of start to say something which can be reproduced also in a more systematic way. And of course, this is what we're all doing, taking our own tools and then kind of using them to expand the knowledge and the area. Yeah. I think that's important. Yeah. Yeah.
And when you heard Jakob's presentation, Seda, what were you thinking in terms of what we've just heard about shape?
Yes, in Jakob's study, I think working on fields and looking at what people, how people are living their daily lives, what's their lifestyle, what their traditions are, looking at that lived experience, I think, is very valuable. And then, yes, it can be, for example, by photographing them, like you showed a very nice photograph with mother cooking, and then kid is sleeping very close to it, so affected by smoke. So that picture, I think, is telling the entire aim of the research of Jakob. So we can use photography, we can use our own observations, so researchers' observation, what we are observing in people's houses, or we can use surveys, questionnaires, we can do some interviews and ask people. So we have, I think, very nice methods to do field studies and to look at experience of people. But then these methods, I think, should be very interdisciplinary. I think that's the key. Yes.
Maybe I can explain, because also what I didn't show here is that we've also used artists and we've used filmmakers, different filmmakers, and we've used photos very deliberate as a way of communicating across disciplinary. Because, you know, you can make a scientific report, but that's kind of, it's not everybody reading a scientific report, but a photo or a video at the right time will actually open more doors. So we've hired people very actively and kind of giving them free hands also to interpret our work and come up with other discussions about it. So this is a kind of a more artistic side to it also.
Yeah, because I was thinking part of what is also so amazingly relevant with your presentation is actually your finishing slide, with just how many houses or homes will have to be built in the next few years. But there is the cultural element or the intercultural element, which is very stark. Because we heard yesterday that indoor climate in private homes is actually is not very good, even in European homes. But the contrast to what you demonstrate in the pictures is quite stark. However, I was also thinking how to mediate or disseminate or explain the knowledge that you accumulate through your architectural work to the other professions in the collaboration. So I think it's nice to hear the...
Yeah. So we try to do it in many different ways. We also try to disseminate it to the people who are using the houses and also potential to the people who need to build the houses and to a kind of, you could say, a wider profession. So at the moment we have been working with telephone apps, kind of small programs where you could demonstrate it, because telephones are what's being used in Africa to disseminate knowledge. Is not kind of completely working yet, but there is a kind of an ambition to be able to demonstrate how to build and to use the principles. I mean, we're talking, for us it's very, so we build these houses from strict principles, but that's because it's a research project. In fact, we could build them in any material or in any shape, but we just built a lot of them in the same shape because we needed to demonstrate what is the effect. But it's important for us to kind of get to the next level also to kind of show how they could be used in different ways. That's kind of the next step.
Yeah. Because that's actually also one of the questions, and thank you very much but we actually have a question to you, Jakob. How can this model be scaled if the materials used are not local and if the architects are flown in from Thailand? I'm sure you gave it some thought.
Actually, it was not architects flown in from Thailand, it was carpenters. So we took a couple of carpenters and placed them in a village, and we didn't ask them to do we asked them to be inspired by our building, but then gave them free hand. So it was actually another way of working as an architect, actually leaving, kind of backing out. But of course it's right that not all buildings have to be built in steel, but it's actually a very efficient way to build also in Africa. But we have already built in bricks, and we've built in wood, and we've built in all the traditional materials. And we can build, I mean, what's most important for us is that, you know, you raise the bedroom, that's kind of rule number one, and then you make these very big openings, use these materials. But again, it can be done in a number of ways. Yeah. We have drawings, for instance, on how to do it as a kind of more suburban areas, kind of like row housing and these have not been built yet, but we have a number of kind of iterations we could do. We're just looking for new opportunities. Yeah,
because you told me earlier today that the evidence-based research, the way that you collected data and then all of a sudden were able to demonstrate based on evidence the effect of the houses, that actually accumulated throughout the project. Can you take us through some of the phases? Did it start out deliberately to be hardcore evidence-based?
Actually, we started as a protest. I think maybe it's a good story. So there was this researcher, a biologist, who was writing a letter in the Lancet saying, where they were testing ways to close the house for mosquitoes not to enter. So we replied to this saying, it's probably not a good idea because it will kind of prevent ventilation. And so we made this answer, and Lancet, they didn't take it, and we kind of got mad and said, this is not right. So then we saw this place where you could apply for money, and we applied for money and got for the first funding, and we saw, so let's kind of find out what is the difference between these open Asian houses and African, and tell something systematic. So that was the first step, to kind of understand the basics. And then we kind of started modeling later, and then we come to the step where we kind of looked at individual components of the building, like windows and doors. and then went back to kind of looking at it as a complete system. And of course, every time you open one of these doors, a new one is opening. What I didn't show, for instance, is that we also looked at behavior. So, for instance, we had these doors opening and closing, so we couldn't understand that there was so many mosquitoes in some of the houses, and it turned out that people were walking in and out of the house all night. So this knowledge has been used, for instance, to modify the doors, so now they are self-closing. So we try to use this knowledge and also try to invent doors where the behavior is not important for people. So we try to make passive design in a way so the behavior is not too important. Because I think that's also one of the links to what you're looking for, that a lot of it comes down to behavior when we talk about how to improve indoor climate in houses. But at the same time, that's also a challenge because how can you actually make sure that people are using it in the way you intended?
Yeah, exactly.
So the more you can kind of rely on passive methods, the better. Also, we are not using any active methods like pumping air around or doing stuff. The only active thing we have is the springs in the doors. So, yeah.
And throughout the research, which is kind of growing and accumulating, apart from the door, has there been any kind of surprises that really kind of blew you away?
Yeah, I mentioned this project where we looked at doors. So this was actually a major project in the Gambia where we rebuilt almost 400 houses, tried to improve them, build better doors and better windows, and try to increase indoor comfort for people to use a bed net. And then we measured malaria directly in the houses. We improved and compared it to other houses. It was a big project. And after working on this in 3 years, we couldn't demonstrate any effect. So it didn't work. So our houses, they might have been a bit more comfortable to stay in, but people were not more healthy. So that was a disappointment. And one of the things we took back was that kind of the interventions we made, the doors we made, and these were locally made doors, they were just of a very poor quality. We couldn't get them right. So the screening was breaking all the time, and they were kind of falling off. And so this led to the next generation where we tried to improve these doors and actually work with a more industrial type of doors. So that's another example of every time you try to look into something, it kind of it leads to the next phase. We are still working on this. We made a new generation of doors which worked very well. We did this with an American company related to this Bill Gates Foundation. And they kind of gave us money to do this, and we hope that we can expand this at some time. And because there's actually a huge need for industrial components like windows and doors in general. If somebody here in the audience wants to make a good living, they invent good doors and windows for Africa, because 2 billion houses or houses for 2 billion people needs to be built, and there's a huge need for industrial components which are affordable and kind of easily to build with. At the moment, most things are made by hand, and of course that's highly inefficient. So there's a need for a lot of development there.
We'll take another question from the audience. First of all, praise, beautiful work to you, Jakob. Did you test building with heavy materials with a big thermal inertia to see if it would perform better, like rammed earth?
Yeah. So if you are in a humid tropical climate, it's never a good idea to have a huge thermal mass. That's what we have in the Gambia, for instance, where you have these houses made from solid blocks, and they are always incredibly hot. So that's the learning from Thailand, you can say, where you have a similar tropical area with raised houses and light materials. It's performing far better when you're talking about natural ventilation if you have a low thermal mass. So it will work, a high thermal mass, if you are in a kind of an area where you have a higher difference between night and day temperature. But if you're just around the equator, it's not good.
Yeah. Hope that was a good answer or a satisfactory answer. Otherwise, please pose another question. And we have a question, I think you may have already touched upon it. What are the future plans with these test houses? Making a business out of selling them, training locals to build them themselves, or something completely different?
So we have now a PhD student at the Royal Academy who is part of this next phase. And he's looking at the performance of the houses and all kind of indoor climate parameters. But he's also looking at how to scale up these things, trying to connect to business, trying to connect to discuss this. One of the challenges is that there's in many parts of Africa is lacking the financial systems to build a house at one time. So they're built typically incremental, and that's a huge challenge. So I would say the challenge is probably more on the financial side than on the technical side. But it would be really nice to get it going. And there's a huge, we get a lot of interest from all kind of organizations and institutions. So definitely it will be possible to build many more.
And just another question has arrived. How do we scale this and cut cost 30% or more? And can we reverse this innovation into our cities of, for example, Europe?
Yeah.
Tough question.
It's tough. You could also say what happened to the building culture of Europe in the past years. So we are using more and more money on solving some problems, and we are creating new problems all the time. So when we talk about affordable buildings, what is it? So we are spending so much money in saving the last 10% of energy, at the same time increasing cost and footprint a lot. So I think there's some balances there where we need to rethink what we are doing. And I would say also from a sustainability point of view, we really have to think about the complexity of buildings, because we are reaching a place where they're so complex that we can't really, it's also come to the point where they become so incredibly different to take apart, where it used to be a wall like this in the building we're standing in, it's probably solid bricks, and a similar wall today would have 8 different layers of materials that are kind of almost impossible to separate. Yeah. So I think it's a very tough question, but it's something we all need to think about.
And I know you've looked into CO2 neutral buildings in some of your previous research, so I'm thinking possibly you have a comment to that as well.
Yes, yes, of course. I mean, these houses can be done, I think, in Europe as well as I mean, if we are simple enough to as Jakob said, simple enough to produce them. And yes, I mean, they should be healthy. So first, I mean, our principle when we decide building them, so we should build them and design and build them and then operate them during their life cycle to make them healthy, energy efficient. Yes, then nearly zero energy buildings is the key, and smart, so that the energy efficiency and the health and well-being conditions can be maintained with the together side by side by the user interaction. And then as Jakob mentioned it before, that I mean, are we really, user behavior is difficult, is a difficult area, because are we really, I mean, do users, as we are users as well in our daily life. So do we really know how to use the systems? For example, if I'm living in a smart house, do I really know how to operate the roof light, the doors, the lighting, the curtains? I mean, then I think a training, a feedback is very important. That should be given to the user. And also, I think user acceptance, acceptability, and friendliness is important. And then I think it's again goes back to simplicity. I mean, the systems should be simple so that users can in a friendly way interact with it, use with it. Sometimes we see some dashboards, but I mean, with lots of buttons, lots of indications. If no one tells you and gives you a previous training, you wouldn't know where to push, and then maybe you are wasting more energy than it should be. So
you've actually just answered a question addressed to you in terms of how data collected in buildings can be used to improve well-being indoors in practice. But there is another question that has just come in, which I think you'll find interesting. What are the future integration plans with SHAPE? Will this be used for developing countries? Now, that could be a link between the your research projects?
Yes. I mean, at the moment in our project, we don't have the affordability component, but yes, it can be integrated. So I just in a second I said like health, energy efficiency, smartness, and then yes, affordability, and then yes, producing it in a good quality, high quality way. So as a industrial production, then yes, it can be done in developing countries as well. Because the people are a key component of our project. So it's a human-centered project. So I think yes, people are living in their houses. So it can be built. As Jakob agrees. So, yes.
We look forward to following your research and see the implications and also application to that. Thank you to you both. It has been absolutely formidable and a huge pleasure.